Hello everyone. Thank you for taking interest in this course. This course is provided by Nirvana Foundation. Presented by B.S. Govardhan. Welcome you all to the second session of our course on solar photovoltaics. Solar radiation and meteorology. Solar radiation prediction is essential for efficient and reliable solar power project and design. Meteorological data such as solar radiation, ambient temperature, relative humidity, wind speed, air pressure, and sunshine duration are accepted as dependable and widely variable renewable energy resources. These data play a very important role in photovoltaic systems. In this course, you will be learning about Introduction to Solar Radiation and Meteorology, GHI, DNI, DHI. Solar irradiation data of Indian cities month-wise. NASA meteorology. Solar spectrum. Solar maps. The map shows the solar irradiance across different regions in India. India is endowed with rich solar energy resource. The average intensity of solar radiation received on India is 200 megawatt per kilometer square. Such maps are often used to derive the potential for solar electricity generation in a particular region. Rajasthan and Jammu and Kashmir receives the highest amount of solar radiation in India. Due to microclimate and topographical differences, changes in location of a few 100 kilometers can result in a change of hundreds of annual sunshine hours. Having selected potential sites based on resource maps and other criteria, access, distance to grid, climate, etc. These locations need to be evaluated by making high-quality on-site measurements of the solar radiation over at least a full year. Current solar radiation and meteorological measurements, and a historical database, can be used in conjunction with satellite data and weather forecasts as inputs to now forecasting models for the output of the plant. This is of particular interest to grid operators, as other power generation sources cannot be switched in instantly when clouds pass over the solar energy plant. Global solar irradiance. Electrical energy produced by a photovoltaic system depends on several external factors. Foremost of these is the amount of solar radiation falling on the surface of the PV modules. Irradiance is the amount of light energy from one thing hitting a square meter of another each second. Global solar radiation is the sum of direct, diffuse, and reflected solar radiation. Depending on geographical location and season, solar radiation or isolation varies between 6.6 kWh per meter square 4.4 kWh per meter square per day. Bangalore in South India receives about 5.4 kWh per meter square per day annual average. All the data will be available on NASA website when latitude and longitude of the geographical region is given. Annual solar energy generation graph month-wise. Global mean solar irradiance. Global map of global radiation across the globe is shown. A number of commercial firms now exist to provide solar resource data to solar power developers, including 3E, Clean Power Research, Solargis, Visala, previously 3-tier, and Vortex. And these firms have often provided solar potential maps for free. Good quality, reliable radiation data is extremely important for all activities in the solar energy sector. Difference between solar irradiance and solar insolation. Solar irradiance. The solar irradiance is the output of light energy from the entire disk of the sun, measured at the Earth. Solar irradiation is the amount of energy per meter square per second expressed in watts per meter square. It is the power of the sun, or instantaneous energy. Solar insolation. Insolation is the total solar radiation that reaches the Earth's surface. Solar insolation is the amount of energy per meter square, over a duration. Can be per hour or per day and is normally expressed in kilowatt-hour per meter square per day or per hour. Solar insolation is measured with the pyranometer. Global Horizontal Index (GHI). Global horizontal irradiance is the total amount of short-wave radiation received from above by a horizontal surface. This value is of particular interest to photovoltaic installations and includes both direct normal irradiance, DNI, and diffuse horizontal irradiance, DHI. Pyranometer. An instrument used to measure solar irradiance on a level surface from a field of view of 180 degrees. Based on the Seebeck or thermoelectric effect, a pyranometer is operated based on the measurement of a temperature difference between a clear surface and a dark surface. The black coating on the thermopile sensor absorbs solar radiation, while the clear surface reflects it. Hence, less heat is absorbed on the clear surface. The direction is sometimes set at an angle, for instance, in solar power applications where the pyranometer is aligned with the orientation of solar panels. In this application, the assessed quantity is called the global tilted irradiance, GTI, shown in first picture. On most occasions, the plane of interest for a pyranometer is horizontal, so that the field of view matches the sky. In this orientation, the assessed quantity is known as global horizontal irradiance, GHI, shown in second picture. A complete solar monitoring station consists of a pyrheliometer mounted on an automatic sun tracker for measurements of DNI, a shaded pyranometer for measurements of DHI and an unshaded pyranometer for measuring GHI, plus a high-performance data logger to acquire and store the measured values. DNI. Direct normal irradiance is the amount of solar radiation received per unit area by a surface that is always held perpendicular, or normal, to the rays that come in a straight line from the direction of the sun at its current position in the sky. Typically, you can maximize the amount of irradiance annually received by a surface by keeping it normal to incoming radiation. This quantity is of particular interest to concentrating solar thermal installations and installations that track the position of the sun. Pyrheliometer. An instrument used to measure direct normal irradiance, DNI, which is designed with a solar tracking system to keep the instrument aimed directly at the sun. Traditionally, pyrheliometers were mainly used for climatological research and weather monitoring purposes. However, recent worldwide interest in solar energy has also led to an increased interest in pyrheliometers. A pyrheliometer needs to be mounted on a solar tracker, a device that points the instrument at the sun throughout the day. To point a pyrheliometer at the sun, a solar tracker rotates around two axes, the zenith, up and down, and the azimuth, east to west, axis. The required position is calculated from GPS coordinates and time, using a solar position algorithm. In the solar energy industry, pyrheliometers, again combined with pyranometer measurements, are used to monitor the performance of photovoltaic, PV, power plants. By comparing the actual power output from the PV power plant to the expected output based on solar radiation data, the efficiency of the PV power plant can be determined. Pyrheliometers can also be used to determine the suitability of potential sites for PV power plants. In this case, pyrheliometers are used to determine the expected output of a PV installation. For PV installations that use concentrated sunlight, monitoring the direct solar radiation is necessary to ensure proper operation of the plant. Finally, a pyrheliometer provides the most accurate method of measuring sunshine duration. DHI. Diffuse horizontal irradiance is the amount of radiation received per unit area by a surface, not subject to any shade or shadow, that does not arrive on a direct path from the sun, but has been scattered by molecules and particles in the atmosphere and comes equally from all directions. DHI is typically measured with a pyranometer. However, in this case the direct light of the sun is blocked in order to remove the beam component of the radiation. The pyranometer may also be shaded by a horizontal or vertical shade band, the former requiring no tracker, the latter requiring a horizontal tracker. However, shade bands are generally less accurate as they remove some of the diffuse light. This diffuse light should be measured and corrected by a location and time-dependent correction factor. Accurate solar radiation measured by radiometers. Radiometer sonde is used for simultaneously measuring the downward and upward broadband fluxes of shortwave and longwave radiation. The radiometer sonde contains a built-in Raman sonde for simultaneously measuring air temperature, humidity and wind profiles. A table of month-wise solar irradiation data for Indian cities measured in kilowatt-hour per meter square per day onto a horizontal surface is shown. The daily average global radiation is around 5 kilowatt-hour per meter square in north, eastern and hilly areas to about 7 kilowatt-hour per meter square in western regions and cold desert areas. Optimal sizing of PV electricity generating system is generally followed by an appropriate study of the location where the unit is going to be installed. Studies related to the performance analysis of PV system at any location requires long-term solar radiation data. This table will be utilized for estimating the feasibility analysis of PV systems over a particular city. You can multiply this irradiance figure by the wattage of your photovoltaic panels to give you an average daily amount of energy you can expect to generate with your system, measured in watt-hours. Three-tier services resource maps broadly available to illustrate the potential of renewable energy around the globe. The maps are regularly published for a wide variety of media, academic, governmental, and commercial purposes. The maps are based on the latest science and technology available. As a result, they have become the standard for renewable resource maps. Solar spectrum. The electromagnetic spectral distribution emitted by the Sun or received by a collector or instrument on Earth. Sun's total energy is composed of 7% UV radiation, 47% visible radiation, 46% infrared radiation. Photovoltaic cells primarily use visible radiation. This figure shows the solar radiation spectrum for direct light at both the top of the Earth's atmosphere and at sea level. These curves are based on NREL data for above the atmosphere and at sea level, which are standards adopted by the photovoltaics industry to ensure consistent test conditions. Regions for ultraviolet, visible, and infrared light are indicated. Distribution of colors within the light. PV cells produce different amounts of current depending on the various colors of light shining on it. The three relevant bands, or ranges, along the solar radiation spectrum are ultraviolet, visible, PAR, and infrared. Of the light that reaches Earth's surface, infrared radiation makes up 53%, while visible light provides 44%. Ultraviolet radiation makes up just over 3% of the total solar radiation. Each of these bands has a different impact on the environment. Solar irradiance in a day. The average daily solar insolation in units of kilowatt-hour per meter square per day is sometimes referred to as peak sun hours. The term peak sun hours refers to the solar insolation which a particular location would receive if the sun were shining at its maximum value for a certain number of hours. Since the peak solar radiation is 1 kW per meter square, the number of peak sun hours is numerically identical to the average daily solar insolation. For example, a location that receives 8 kWh per meter square per day can be said to have received 8 hours of sun per day at 1 kW per meter square. Being able to calculate the peak sun hours is useful because PV modules are often rated at an input rating of 1 kW per meter square. Solar radiation components, global, beam and diffused. Graph shows solar radiation in a sunny day. On this graph you can see the part of the irradiance coming directly from the sun and the part coming from the sky is diffused radiation. The solar radiation that is emitted from the sun in the form of electromagnetic waves, entering the atmosphere is filtered by the gases it contains, mainly by clouds that are floating, which bounce the light to operate as mirrors. When passing a cloud, global radiation decreases dramatically and diffuse radiation increases as a result of the deviation in the direction of the axis of light that causes the cloud. Solar path. Figure shows the orbit of the Earth around the Sun. As the Earth moves around the Sun, its axis maintains a nearly constant orientation in space. Earth rotates around the Sun, it is tilted on an axis. The tilted rotation impacts the position of the Sun throughout the year. This tilt gives us the seasons. In the northern hemisphere, the longest day is the June solstice, and the shortest day is the December solstice. The opposite is true in the southern hemisphere. In the northern hemisphere, the summer solstice occurs on June 20th or 21 and the winter solstice on December 21st or 22. The situation is exactly the opposition in the southern hemisphere, where the seasons are reversed. Figure shows the apparent path of the Sun across the sky. In summer, the Sun's path is longest, and so are the days. In winter, the Sun's path is shortest, and so are the days. The longest day will occur on June 21st. The shortest day will occur on December 21st. Performance of solar panel. Various factors that affect power output from panels. Shade or clouds. Shade is the enemy of solar because much like clouds it is blocking the sunlight required to produce electricity. As soon as your panels are out in the open in the clean air, or not so clean air, dust will start to settle on them, blocking sunlight, reducing their efficiency. Panel position or angle. Active panels can track the sun, temperature and solar irradiance variations. Believe it or not, warmer temperatures actually have an adverse effect on the production of solar panels. For daily production, high temperatures cause a drop in voltage and, in turn, a drop in power. Sun intensity is directly related to the power production. As it increases, solar production increases as well. Air gap required for cooling. Even the best solar panels can have their efficiency significantly impeded by environmental factors, though with proper design, most if not all of these factors can be mitigated. Sun altitude. The altitude of the Sun is simply a measurement of how high it appears above the horizon, in terms of an angular measurement. It is denoted by alpha. If the Sun were directly overhead, it would be at an altitude of 90 O, since a full circle is 360 O, and from the horizon to directly overhead is 1/4 of a full circle. The altitude is 0 at sunrise and sunset, and can reach a maximum of 90 degrees, directly overhead, at noon at latitudes near the equator. The altitude of the Sun varies throughout the day, but it reaches its maximum altitude around noontime. Sun azimuth. The azimuth angle is the compass direction from which the sunlight is coming. At solar noon, the Sun is always directly south in the northern hemisphere and directly north in the southern hemisphere. The azimuth angle varies throughout the day as shown in the picture. It is the angle between the normal to the surface and south. Azimuth angle is denoted by gamma. For south-facing surface azimuth equals 0. For north-facing surface azimuth equals 90 degree. In general, the azimuth angle varies with the latitude and time of year. Solar zenith angle. It is complementary angle of solar altitude angle. Solar zenith angle is the angle at which the sunlight strikes a particular location on Earth. It is denoted by Z. This angle is 0 degree when the Sun is directly overhead and increase as sun sets and reaches 90 degree when the Sun is on the horizon. The larger the solar zenith angle, the weaker the insolation, because the same amount of sunlight has to be spread over a larger area. When the zenith angle is large, sunlight has to pass through a thicker layer of the atmosphere before it reaches the surface. Optimum tilt. Maximizing solar radiation is the main target to change the tilt angle in any solar energy system. The optimum tilt angle is low in the summer and spring, high in the winter and autumn, where the lowest optimum tilt angle during the months, May, June, and July, is 0 degrees, and the highest values during the months, November, December, and January, is more than 30 degrees in different countries. The photovoltaic systems are showed a great gain in the systems that used optimum yearly tilt angle, where the tracking system is not the preferred design because in the developing countries there are a leakage in maintenance. If you are going to adjust the tilt of your panels 3 times a year, the best months to do it are when the solar season changes. Summer, February to May. Monsoon, June to September. Winter, October to January. A zero tilt angle means that the face of the panel is aimed directly overhead. A positive tilt angle means that the panel faces more towards the equator. In the northern hemisphere that would mean tilting so it faces towards the south. Rarely, the tilt angle can be negative, this means the panel faces away from the equator. Figure shows the difference in area required with radiation incident normal to the surface versus radiation incident at an angle. The power incident on a PV module depends not only on the power contained in the sunlight, but also on the angle between the module and the sun. When the absorbing surface and the sunlight are perpendicular to each other, the power density on the surface is equal to that of the sunlight. However, as the angle between the sun and a fixed surface is continually changing, the power density on a fixed PV module is less than that of the incident sunlight. For a fixed tilt angle, the maximum power over the course of a year is obtained when the tilt angle is equal to the latitude of the location. PV row spacing. When designing a PV system that is tilted or ground mounted, determining the appropriate spacing between each row can be troublesome. However, it is important to do it right the first time to avoid accidental shading from the modules that are ahead of each row. This can lead to underperforming systems and angry customers. In calculating the inter-row spacing for your modules, the height difference from the back of the module to the surface must be measured. For example, location, Bangalore. Latitude equals 13 degree. Earth tilt angle equals 23.45 degree. 250 watt peak module length equals 2007 millimeters. Sin, 13 degree, equals 0.224. 10, 23.45 degree, equals 0.433. Cos, 13 degree, equals 0.974. Substituting all the values in the L-min equation gives L-min equals 2993 millimeters. Inference. Depending on geographical location and season, solar radiation or isolation in India varies between 6.6 kWh/meter square, 4.4 kWh/meter square per day. Global horizontal irradiance is the total amount of short-wave radiation received from above by a horizontal surface. We have learned about direct normal incidence and diffused horizontal irradiance and how we can measure it. Pyranometer and pyrheliometer working and construction. Solar path, solar window and solar angles, solar altitude, azimuth angle and zenith angle. Optimum tilt angles and spacing of PV panels to obtain maximum efficiencies. Thank you. This is the end of solar radiation and meteorology session. For any queries, visit our website www.nirvanafoundation.com.